Okay, so we're back to Chapter 2, Section 1, and now we're looking at transforming data. So this is where we're really looking at the z-score and how we transformed our information by we took our data point, we subtracted the mean, we divided by the standard deviation, and we were able to standardize all that. So everything would have a mean of 0, a standard deviation of 1, and we could compare a lot easier. The distributions. And so now what we're going to do is we're going to analyze the effects of transformations on a distribution. Now transformations are going to occur when you are going to add, subtract, multiply, or divide all values in a distribution by a certain number. And when we do this, we actually find some patterns that occur. And we learned that if you add or subtract by a constant value, so I'm adding the same number to every value in the distribution, or I'm subtracting a number from every value in the distribution, then what happens is the shape and spread stay exactly the same. So if it's skewed, it's going to stay skewed. And then that spread, because all I'm really doing is I'm taking my little distribution and I'm moving it. So I'm taking that and I'm moving it to the right. If I'm adding, I'm moving it to the left if I'm subtracting. But that shape and spread doesn't change at all. It's still spread the same amount apart. I'm just shifting where it is. So it's kind of like in Algebra 2 when you were doing transformations and you're just like moving your graph up to the right or to the left or down. The shape of that is staying the same. And the shape of it is originally, the shape is staying the same, and that spread, it's not being stretched out or compressed in or anything like that. So what ends up happening is then the center, because the center is an actual location, that will change. And it'll change in the exact same way that we're doing to every little data point in our distribution. Now, if we're going to multiply or divide by a constant, now we're starting to get some of this like stretch compression of our distribution. And our shape will stay the same, but now my center, spread, and location will change by that same multiple or that same division. So we've got a sample problem because it always makes sense when you see it in motion. So we've got some test scores. So we've got a graph and a table of summary statistics for 30 test scores. The maximum score on the test was 50 points. And so when we look at our distribution, we're seeing a left skewed distribution occurring. And we know that there were 30 values, our mean, our standard deviation, our 5-number summary. And then they tell us the range, just so it's just a little bit easier on us. Suppose the teacher decided to be nice and added 5 points to each test score. How would this change your shape, center, and spread of the distribution? So my shape should not change. No matter what we do, the shape shouldn't change at all. Now our center, whether it's our median or our mean, that should change the same way this is. That should add 5 points. So my mean would now be 35.8 plus that 5. So it would now be 40.8. The median would change by adding 5 also. So I'd add 5 to 37 and get 42. So both of those would add 5. Now our spread, because I'm just adding, so I'm just shifting it to the right, I'm adding 5, that spread does not change. And that spread would be our standard deviation. or IQR. Neither one of them would change. They would be exactly the same. Okay, suppose the teacher wanted to convert the original test score, not the extra 5 points, but the original test score from our distribution, these scores right here, to percents. Since the test was out of 50 points, how would this change the shape, center, and spread of the distribution? So to make it a percentage, I would make it out of 100 points. So I would go ahead and times each value by 2. So how that would change my shape? Shape would stay the same. If it's skewed to begin with, it's going to be skewed after I transform it. Our center would be multiplied by 2. So that would look like my mean would be 35.8 times 2. So 71.6. It's supposed to be 71.6. Okay. And then our median would do the same thing. I times it by 2, so that's another measure of center. So 37 times 2 would give me 74. And so we can use these rules instead of having to change every single number in the distribution. I can use this rule to help find a new mean, a new median, a new IQR, all of that. Now our spread, because we are timesing, the spread does actually change. And my spread will times by 2 also. So my standard deviation, I would times by 2. So 8.17, I can't do in my head, times 2. Yeah, I should have been able to, 16.34. And then our IQR, well, we'd have to find the original IQR, there we go, 9. So that would times by 2. So our spread would get bigger. And that's it. That's how we transform. So keep in mind, add and subtract, we only change the center. Multiply and divide, we change the center and our spread. When combining transformations, sometimes we can use an equation to help decide what is happening. So we can solve the equation for the other variable, apply them. So we have this little situation, we've got taxi cabs. In 2010, taxi cabs in New York City are charged an initial fee of $2.50 and an additional $2 for every mile they traveled. In the equation form, it looks like this. Well, if I wanted to know the distribution of the fare based on the distribution of my miles, I could actually work this out here. So if I want to, actually, I know the distribution of the fare. So I know the mean fare was 1545 and the mean standard deviation was 1020. So if I want to figure out what's happening with miles, I need to take this fare equals 2.5 plus 2m, and I need to solve for m because I need to figure out what's actually happening there. So I need to undo everything that was done to get the fare. So I'm going to start by subtracting 2.5 on both sides. So then I have the fare minus 2.5. And then I would divide by 2. And that allows me to have an equation for my miles. So I figure out what I have to do to fares to transform and figure out what's happening with my mileage. So my mean, I would go ahead and actually take the mean fare 15.45 and minus 2.5 and then divide by 2. And that would give me my new mean. Of 6.475. So on average, people are traveling 6.475 miles, about 6.5 miles. But now, when I want to calculate standard deviation, I have to be careful, because when I transform data, with adding and subtracting does not affect standard deviation, which is a form of spread. So if I want to do this, I would take that standard deviation and I would not subtract that 2.5 because adding and subtracting does not affect my standard deviation. The only thing that affects is multiplying or dividing. So this will give me my new standard deviation. Just the 10.2 divided by 2. And so I'd get a standard deviation of 5.1 miles. And that's it. And so this is kind of the trickiest part, is remembering what applies to what. We only multiply and divide with our standard deviations, or when we're using standard deviations in our calculation. And we will add, subtract, and multiply, divide with our means. Okay, we've talked about density curves before, and that's just kind of guiding us on how to kind of create a curve over our distribution. So approximately 100% of our data values are going to be below that curve. And with this curve, we're kind of showing how some of this empty space here is really taken up by this there, and so we kind of use that to help guide us. But yeah, that smooth curve, and you can be more exact with density curves, but really we're just kind of sketching it out to get an idea of what's happening in a shape. Now, some things to remind yourself about a density curve. It will always be above the horizontal axis, so it will never go below this x-axis here. A density curve will always have an area of 1. Always and forever. So that means that really all the values should be under there. And as we talk about this area under the curve, we're actually going to use this to help calculate the probability. So what's the probability that it lies in this region or that region? And we use the area to represent probability. Density curves can come in many shapes. They can be skewed, they can be symmetric, they can be bimodal, but we're going to look mainly at our symmetrical in this chapter, but we'll also be looking later on in the year at more skewed data too. No set of data is described exactly by a density curve. Again, it's just kind of an approximation, but it's an approximation that is easy and accurate enough. So in stats, it's all about being just accurate enough. Nothing is truly exact when we're using statistics. And that's kind of the hard part for people who are real math people. They want everything to be exact and all that sort of stuff. And it's not. It's not an exact science. It is all an estimation of what's truly happening in the world, because we can't really measure everything that's truly happening in the world. Now, just a reminder of something else that we talked about in Chapter 1 is talking about mean and median of the curve or the distribution. And I wanted to remind you that your median will cut your curve into 2 equal areas. So when I'm looking at this curve here, this is my median because this area here is equal to this area here. Now your mean is going to be the balance point. So if it was made of solid material, where you'd have to put your little point so that way it would balance nicely on here. So here, this is a little too far away. This is a little too far on this side. and this would be right in between. Please remember that if your distribution is symmetric, your mean and median will be the same. But if it's skewed, your mean will be pulled towards the tail. Not always a lot. Sometimes there's just a small difference there, depending on how skewed it is. Now, there is a website that I want you to take a chance to take a look at. It's listed down here. And if you have the right... So go ahead and go to that website. The link is also on the web page. And feel free to check that out. You can sit there and play with the distribution and try and figure out where the mean and median is. And we'll see you next week.